People have been arguing for centuries that 0.9 recurring can't equal 1. This might be because we can produce a pretty good argument against any proof that 0.9 recurring equals 1. And we will examine one of those arguments now. Another really popular argument is called the algebraic proof, and it goes like this. Let x equal 0.9 recurring. So 10x is 9.9 recurring. Then we subtract the first line from the second, giving 9x equals 9. And so x must equal 1. This might look very clever, but just think about what's really going on here. We start with x equals 0.9 recurring, then all we do is simply multiply both sides by 10 minus 1 divided by 9, which is the same as multiplying both sides by 1. So we should end up with exactly what we started with. It shouldn't change to x equals 1. If we multiply both sides by 9 over 9, we get 9x over 9 on one side and 8.9 recurring over 9 on the other. And so this time we do end up with exactly what we started with. Now let's consider the difference between the two approaches. It all comes down to what is 0.9 recurring times 10 minus 1. Does it equal 8.9 recurring, or does it equal 9? The question is, can the subtraction operation somehow get rid of the endless terms? If we work with the series instead of the decimal, we write it down again and note the one-to-one correspondence between the terms of the series, then we multiply the top line by 10. Note that each term of the series gets multiplied by 10, and we keep the one-to-one correspondence with the original terms. Now we do the subtraction, and the resulting series on the right-hand side is 81 over 10 plus 81 over 100 and so on. It is not the number 9. This would appear to correspond to 8.9 recurring in decimal form. In order to get 9, as in the so-called algebraic proof, we would have to shift the terms, breaking the one-to-one correspondence. And we would have to believe that we can match all of the original terms with all the original terms apart from the first term. But can we really do this? We could test if this logic is correct if we could find a case where the trailing part cancels out in both scenarios, when we shift the terms and when we don't shift the terms. And this series, 1 plus 1 plus 1 and so on, just happens to fit the bill. On the left hand side, we won't shift the terms, and on the right hand side we will. We'll shift by one place, as in the proof. We'll do the subtractions, and we end up with 0 equals 1, which is a clear contradiction. And so this appears to indicate that we can't match the original terms with one less than the original terms. In which case, the algebraic proof is flawed and it doesn't prove that 0.9 recurring equals 1. Yet again, the mathematicians will claim that we're not following their rules. But we used the series 1 plus 1 plus 1 etc. to test the logic of matching all the original terms with one less than all the original terms in a subtraction. The only thing that's relevant to the cancelling out is that the series is endless. All of these series are simple geometric series, and so all of them have the same structure in that they just have different first terms and common ratios. And so we stand by our argument that the shift and subtract logic is completely invalid. But the mathematicians will claim that we can't test the logic with a divergent series. It seems like they are still just choosing to rule out any logic that highlights a problem with their precious real numbers. In fact, it could be argued that every convergent series contains a divergent series hidden within it, if we allow regrouping of the terms, then even a converging series like 0.3 recurring can be easily converted into 3 series, such as 1 plus 1 plus 1 and so on, minus 1 minus 1 minus 1 and so on, and the original series. Then we can line up the terms at different offsets, making the whole thing tend towards different values, such as 1 1/3, or 2 1/3, and so on. If sequences and series have real-world meanings, then this would come as no surprise, because obviously any rearrangement of terms will change the real-world meaning of a series or sequence. The mathematicians will say that 3/10 plus 3/100 and so on is an absolutely convergent series, and we would only be able to make it converge to different values if it were conditionally convergent, because then the Riemann rearrangement theorem would apply. They are effectively saying that it's fine to rearrange terms as long as it can't be viewed as changing the series from one of their categorizations to another one of their made-up categorizations. In fact, rearrangement can even make a series diverge. So surely we can't claim that the different series are fundamentally different kinds of objects just by placing them into different classifications, especially when it's so easy to drift across these made-up classifications by simply rearranging the terms. Finally, thank you for taking the time to watch, and I hope you enjoy my other videos.